Okay, this is calculus. We are now in chapter 4, and we're going to move around through a few chapters in this section, but we're going to really focus on the derivative now. We are no longer going to use our limit definition of the derivative. Instead, we're going to find some general rules that will apply and that will help us find the derivative easier and faster. Okay, so I'm going to start and teach you a bunch of the rules. First of all, the derivative of a constant. Just to refresh our memory, I'm going to go ahead and use the definition of the derivative that uses that limit. We're taking the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. Now, if you have a constant, this is a constant function, so f of x equals, say, 3, or some other constant. Just by the definition of the word constant and the idea that a derivative is measuring how something changes or a rate of change, we know that a rate of change of something that's constant should be 0. And I'm going to show you that that's how this limit works out. So let's do the specific example when y equals 3. Then what is f of x plus delta x? Well, it doesn't matter what x is. The output's always 3. So if my input is x plus delta x, my output is 3. If my input is x, then f of x is 3. And so I get 3 minus 3 over delta x. And this is 0 divided by delta x. And 0 divided by delta x is 0. So I'm taking the limit as delta x approaches 0 of 0, but there's no delta x anymore to plug into, so this answer is 0. So this is our very first rule. The derivative of a constant equals 0. Our second rule is the power rule. So I know before you guys had a function like f of x equals x cubed, and you would have to do that limit. And then it would take about a half of a page, and eventually your answer was 3x squared. And I always knew what the answer should be because I understand the shortcuts. It turns out that if you have x to a power n, where n is any number at all, positive or negative, or 0, or because that would be a constant, or a fraction, then the derivative is n times x to the n minus 1. So this, in the example of x cubed, the 3 is now in the front. We have 3x, and now instead of a 3, I have 3 minus 1, which is 2. And so here are a bunch of examples. What about if f of x is x squared? Well, then f prime of x is 2 times x to the 1. What about if f of x is x to the 23,162? Then my derivative is 23,162 times x to the 23,161. So I'm just using that power rule over and over again. Okay, and my last two examples here says 1, 2, 3, 4. And number 3, I don't see a power. Well, you need to rewrite f of x so that you do see a power. Remember, a radical is a fractional exponent. So I'm not taking the derivative. Notice I'm writing f of x here. F of x is x to the 1/2. What about f prime of x? Well, now that I see that this is x to a power 1/2, I use my power rule. So I get 1/2 x to the 1/2, and I'm supposed to subtract 1. Well, what is 1/2 minus 1? That is negative 1/2. And now I want you to be able to rewrite this again. What is x to the negative 1/2 power? Well, that's 1 over x to the positive 1/2 power. And a 1/2 power is a radical. And so this derivative turns out to be 1 over 2 radical x. And we did this before. We have done this question. If f of x equals radical x, we have determined that f prime of x is 1 over 2 radical x. But we just did it with half of a page worth of work because we did a limit. And now finally, number 4. Again, you're going to rewrite this because this is a fraction to start with. It's not x to a power. There is an x to a power down here, but I need to rewrite this overall as x to the negative 8 power. Now I'm going to do my power rule when I take the derivative. So I put the exponent in the front, negative 8x, and now my new exponent is my old exponent minus 1. So what's negative 8 minus 1? It's negative 9. And so f prime of x is actually negative 8 over x to the 9th power. Okay, some more rules. The constant multiple rule. This tells me that if I have a constant c times a function, then when I take the derivative, so I'm going to use Leibniz notation here, dy dx, then I just get to keep c in front and then do the derivative of the f of x function like normal. So a constant multiple just stays there. The constant multiple stays. That's different than a constant. The derivative of a constant is 0, but it's not a but you're not a multiple of anything then. Okay, the sum and difference rules. If I have a function added to another function, then the derivative I get to do independently, one by one. You just take the derivative of each thing and keep the plus sign. Same if this were a minus. If I had f minus g, then the derivative would be f prime minus g prime. Okay, so here's my next example. My next examples. I have a bunch of them listed here. Okay, so let's start with A. And so if f of x equals x to the 5th minus 11x to the 3rd plus 62x minus pi, what is f prime of x? I'm going to work that down here. So then f prime of x is going to be, well, my x to the 5th, I've done one like that. That's 5x to the 4th. Now I'm going to use my sum and difference rule. So I'm just going to minus the derivative of the next part. Well, the next part has a constant multiple in the front, 11. So I'm just going to do 11 times, and then what's the derivative of x to the 3rd? That's the power rule, 3x squared. Now plus, I get to do a plus and then do the derivative of my next term, 62 times x. Well, 62 is a constant multiple, so it's 62 times the derivative of x. I don't think we've done the derivative of x yet. That's also the power rule. Remember, there's a 1 power that's to the top of x. And so I would say 1 times x, and then 1 minus 1 is 0. Well, what is x to the 0 power? That is 1. Okay, and now I have minus pi. Pi is the number 3.14159. Keeps going on forever. But this is a constant. And so the derivative of that constant is 0. So I'm going to clean this up a little bit. So for my first example A, f prime of x equals 20x cubed minus 33x squared plus 62x. Okay. B I will do in blue. I didn't leave enough space. And B, you need to rewrite. So we want to rewrite and then do the derivative. I'm going to leave B as an exercise for you to do. Rewrite first. And I'll give you a hint. This radical 4/5, this is going to be x to the 5/4 power, right? Because the root part is the bottom of the fractional exponent. And don't forget to rewrite your x squared in the denominator also. All right, now let's do this third one, C. In C, f of x is a fraction. You don't know how to do fractions yet. This is a quotient. There's a whole special section on quotients. We have to learn the quotient rule. It's actually very difficult. So you can't do this derivative the way it looks right now. It's too difficult. But I can rewrite f of x. This 3x in the denominator will distribute. It will distribute to every term in the numerator. And so when I rewrite C, then f of x is 3x cubed divided by 3x plus 21x divided by 3x minus 9 divided by 3x. This is just the distributive property, but with a divide instead of a times. I haven't done a derivative yet. Notice I'm still labeling this as f. I'm going to cancel things. My first term, this is just x squared. My second term is 7. And my third term, the 9 and the 3 cancel. This is going to be a 3, and I want to rewrite that x as x to the negative 1 power because it's in the denominator. All right, so this is a nice function that I can do the derivative of using my power rule over and over again. So the derivative of x squared is 2x. The derivative of 7 is 0 because that's a constant not multiplied to anything that varies. However, this minus 3x to the negative 1, that minus 3 is a constant multiple. It multiplies to x to the negative 1. And the derivative of x to the negative 1 is negative 1x to the negative 2. So let's clean up this derivative. I have 2x. And negative 3 times negative 1 is a positive 3. And then this is divided by x squared. And there's one more example on this page. D. Okay, D I will also leave for you to do. But D is difficult. You need to cube this. You need to simplify this first before you can do any derivative, because you don't know how to do the derivative when you've got a parenthesis and something different inside. We are going to learn how to do this without FOILing twice, but for now you have to FOIL twice, collect like terms, and then do the derivative from there. So I'm going to check to see that you have done that in your notes. Okay, I have some more example problems. On this question, I have a cubic function, and I want to know where the tangent line is horizontal. This is one of our favorite questions. We want to know where a tangent line is horizontal. Remember, the slope of the tangent line is the same as the derivative, okay? But it's evaluated at a point. So this is a number. Slope of the tangent line is a number, and the derivative is the formula that tells you the slope of any tangent line. Well, tangent lines, the lines that are horizontal means you have a 0 slope. And so what I want to know is, when does y prime equal 0? So the first step in figuring out when y prime equals 0 is to figure out y prime. So I'm going to take the derivative here. At this point, I know 1/3 is a constant multiple, so I'm going to do 1/3 times 3x squared. But I'm going to think of taking this 3 and multiplying it to the 1/3, because that's a little simpler. And I'll get x squared minus 2x plus 3, and then the derivative of 10 is 0. So this is my derivative, which tells me the slope at any tangent line. I want to know when the slope of the tangent line is 0. So I set this equal to 0 and solve. I'll have to do that by factoring. And I get x equals 3, and I get x equals negative 1. I have two solutions. Find the points on the curve. Okay, so one point is the point 3 comma. Well, if x is 3, y would be 1/3 times 27 minus 9 plus 9 plus 10. Is that 19? And then when x is negative 1, to figure out the y value, I need to plug in negative 1. So I get negative 1/3 minus 1 minus 3 plus 10. 10 minus 4 is 6. Negative 1/3 and 6. 6 is 18/3. That's 17/3. So these are the 2 points where the tangent line is horizontal, because the derivative at these two x values is 0. That means the slope of the tangent line is 0. That means the tangent line is horizontal. In this example, I'm finding the equation of a tangent line. So to find the equation of the tangent line at a point, I know how to find the equation of a line. I do y minus y1 equals m times x minus x1. I better fix that. This is the x value. That's the y value. Okay, and so the question is, what's the slope? Well, the slope of the tangent line is the derivative. So I'm going to find the derivative, 21x squared minus 5. This is a formula. This is a formula. It will tell you the slope of any tangent line. This is the slope of any tangent line. Do not plug this into M. It is not the slope of this particular tangent line. I only want the tangent line at this point. So I need to plug in when x is 1. At the point where x is 1, the slope is 21 times 1 squared minus 5. The slope is 16. So m is 16. M is not 21x squared minus 5. That's a parabola. If I plug a quadratic in for m, I no longer have a line. M is constant. It is 16 at this spot here in particular. So your answer is y minus 4 equals 16x minus 1. So y equals 16x minus 16 plus 4 minus 12. Okay, I want to show you how to do derivatives on the calculator. On the calculator, I'm going to get out my calculator, and in your graphing page, notice I have typed in the function 7x squared minus 5x plus 2. I think that was our example here. 7x squared minus 5x plus 2. And in this function, you can see it's a cubic. But what I'm going to do is find the derivative when x equals 1. The answer was 16. So that's the slope right here. Okay. I'm going to insert a calculator page, and I'm going to go through the menu. Under menu, you want to choose the calculus menu. Now this is a CAS. None of you have CASs. So the CAS will actually find the derivative in general in terms of x. But I know that all calculators will find the derivative at a point. So you want to choose derivative at a point. Our variable is x, and our value is at x equals 1. Now, what this has done is it's set up a particular thing for you. And this is essentially saying find the derivative of something at x equals 1. And you need to type in what to take the derivative of. I typed this into f1 of x. So I'm going to, for my variables menu, choose f1 and then say x. And notice it gave me 16. You don't have to use the graphing menu to do this. You could run through the calculus menu, choose derivative at a point, variable x value 1, and then just type in manually, what was it, 7x squared minus 5x plus 2. Oh, it must not have been that. It was 7x cubed minus 5x plus 2. Let me fix that. Okay, and you'll get it that way as well. Okay, so that's how you do the derivative on the calculator. Next, let's do one final example. Oh, no. I'm going to briefly talk about this at some point, but we're not going to talk about it today. Rates of change are just the idea that a derivative is a rate of change. And specifically on this page, I'm talking about an object that is moving its position. So that would be something that has velocity. And so I'm going to go, I want you to write this down. So here's the rates of change notes. Go ahead and pause this and write down position, velocity, and acceleration. And then the difference between average rate of change and rate of change. And then when we get to class, we'll talk about the pumpkin falling off the 11-story building. Okay,